In this example, I want to use the same two equations to illustrate how we can find a lot of different areas with the same bounds, or with the same bounds and equations. In this example, I want to find this area. Okay. Now, we of course have a lot of experience doing this with just normal functions, and we're used to doing just top function minus bottom function. And certainly with polar coordinates, there's some thinking that you can just do the outer function minus the inner function. I guess I would kind of urge you to not think about it that way, and instead just think about the shapes on their own, and then maybe thinking about taking the larger, the outside shape or the large shape and subtracting the inside shape. And I think you'll see what I mean as we go with these different examples. I'm going to focus first on the big part. This is the bottom equation, 3 sine theta plus 3. And I would like to go, figure out these two bounds. Now again, remember that the bounds are angles. So we need to figure out what angle has 3 and negative 3. What would we plug into theta to get those two? Now a student that I had a few years ago said that the way she thought about it is like a windshield wiper, and that in polar you're really just sweeping out with the angle, starting at 0 and sweeping out, and that's a good way to maybe start. And I'm actually going to start just thinking about that polar angle of 0. I'm going to plug 0 in for theta. So sine of 0 is 0, 3 times 0 is 0, plus 3 is 3. So the angle 0 does give us an R value of 3. So if I think, okay, I want that to be my first angle. Now my second angle, it kind of looks like it would correspond with, of course, pi, right? Since this line is pi, so I'm going to plug that in. The sine of pi is 0. 3 times 0, 0, plus 3. And remember, in polar coordinates, you're talking about going out along this angle, and we did go out 3 units. So the upper bound is pi. So if I did 1/2 3 sine theta plus 3 squared d theta, that would give me the entire area inside this shape. Okay. Problem is, of course, it would also include this, which I don't want. Okay, I just wanted this part. So now you've got to figure, well, I have the whole thing. I just want to subtract out this. Easiest way to do that, of course, is subtract the other equation, which is also from 0 to pi. So 1/2 from 0 to pi, 3 squared d theta. And doing those two, the first one minus the second one, would give us that red, that big red area. Okay? Now another area you could want to find here, same two shapes, is this. And now, of course, thinking about this again, it's kind of like a windshield washer, as you say, well, I have to sweep from here around. 3, r equals 3, actually gives us the bigger angle. Well, this is pi, and this is 2 pi. So we could set this up as being 1/2 the integral of 3 squared d theta. We're going from pi to 2 pi. But of course, that right there gives us the whole thing. That's not what we want. So I need to subtract out. I'm going to shade this in blue. I need to subtract that out. Well, easy enough to do. Subtract 1/2 the integral from pi to 2 pi of 3 sine theta plus 3 squared d theta. And again, using f and int, you'd be able to do that. Now notice that since they both this example and the previous example have the same bounds, you could condense these. You could bring the 1/2s up front, and you could just do r squared minus r squared. The reason I don't like to do that, you'll see in the next example. let's say that in this example we wanted this area. Okay? That's what we want. Well, the problem is that we saw in the previous two is from 0 to pi, one angle's on top, the other's angles on, or I'm sorry, one equation's on top, the other's on the bottom. And from pi to 2 pi, we have a change of what function creates the shape. So what I would do in this example is think about this as two separate functions, two separate shapes. I'm going to find the area up here, and then I'm going to find the area down here, and I'm going to add the two together. So the first one would be 1/2 0 to pi 3 squared d theta. That'll give me that top shape. The second would be 1/2 from pi to 2 pi, and we go 3 sine theta plus 3 squared d theta. And then I would add those two together. And that's what makes these polar ones kind of different, kind of fun, is they don't work the same as just normal functions, where it's always just top minus bottom. In this case, we actually had to change our thinking a little bit, and I guess similar to when you had a change in with regular functions of what function was on top and bottom, and you had to use two integrals. But here, we actually had to start and say, well, what shape is dictating from 0 to pi? And we basically just integrated that one to get this area, and then we did it again from pi to 2 pi to give us this area, and we added the two together. This was actually on the AP exam a couple of years ago. It was slightly, I think it was different coefficients, but it was actually the same shape.